Okay, I am here is going to share about geotextile. Geotextile are utilized in civil development projects for soil fields to improve soil qualities. Geotextiles make soft soil more sensible, empowering development in places that would some way or another be unsatisfactory. Geotextiles are ideal material for some foundation works, for example, drainage structure, streets, landfills, harbor, and other civil related projects. The advantages for geotextiles are they are lighter in weight. This makes for easier handling and laying on sites. Second, transports and labor costs are less in real terms. Third, knitted geotextile have a high tear strength. Fourth, increase construction progress. And the last one is to improve in structure quality. There are also the advantages for geotextile. First is installation of geotextile is critical and requires experienced contractor. Second, this may delay seed germinations due to reduction in soil temperature. Third, geotextiles have maximum flow rates. Fourth, it is not suitable for areas that have heavy traffic. And last but not least, blankets and mats are not satisfactory for the excessive stony areas.
Okay, let me explain about function of geotextile and types of geotextile. For the function of geotextile reinforcement is when geotextile are inserted into the soil, the tensile strength of the soil can be improved by the same volume of concrete material. Okay, there are two types of geotextile. First, woven geotextile fabrics. Second, non-woven geotextile. For the woven geotextile fabrics, which is created by imprinting techniques that are close to those of regular clothing, are typically found. They have the characteristics existence of two sets of parallel threads or yarns. The yarn that runs parallel is called the warp, and one perpendicular is called the weave. For the non-woven geotextile, at the first, which is steady filament yarn, was made from non-woven geotextile. Secondly, thermal, chemical, mechanical, or a mixture of methods are used to bond fibers. Moreover, 0.5 until 1 mm is the thickness of the field fibers achieved by mechanical interlocking. Finally, non-woven are comparatively approximately on the order of 3 mm when chemically bonded. Okay, let's move to how to install high-strength reinforcement geotextile fabric. Step 1. Prep the root surface. First, the roadway should be excavated to the required elevation. Then, totally compress substrate, making sure all air has been absorbed and the soil absolutely tightened. Step 2. Unroll the reinforcement geotextile fabric. On the compacted subsurface, roll the geotextile fabric to ensure that it is free of wrinkles and falls. As directed by the engineer, overlap fabric. Step 3. Sew the geotextile fabric. This roll allows the fabric on the job site to be stitched. To keep it from untreading, the fabric needs to be sewn with a dual 3-block stitch. Step 4. Apply aggregate. Place the aggregate to the thickness specified, ensuring that no system drives directly to the engineer field. Before the final stage, ensure the field has reached complete compaction. Last but not least, step 5. Lay asphalt. Now the subbase has been placed, ready for the pavement layer or layers depending on the project type.
Let I proceed about geogrid. First thing first, what is geogrid? Geogrid is a polymeric material made up of many polymers like polyethylene, polyvinyl alcohol, polypropylene, and many more. It is one of the most important inventions in geosynthesis, which is used as reinforcing material. They form by joining intersecting ribs. They have large open spaces in between the ribs, known as apertures. There are 5 advantages of geogrids, which is the use of geogrids result in a more economical construction. It is environmental friendly. Imparting geogrids makes the members more durable since it resists environmental attacks. It prevents the soil from erosion. And lastly, geogrids ensure ease of construction as the placement techniques are simple. When there are advantages, there also will have the disadvantages of geogrids, which is clogging of geogrids is a challenging design for certain soil types or unusual situations. For example, loose soil, fine cohesion, less silt, highly turbid liquids and microorganism-laden liquids, run-off water are troublesome and generally require specialized testing evaluation. And lastly is Handling, storage, and installation must be assured by careful quality control and quality assurance. Next, I will share with you guys common application of geogrids. Firstly is retaining walls. The advantages of geogrid in retaining wall resulted in the further use of geogrids in many structures like pavements, dams, and many more, and it was found very much suitable due to its property of distributing load over a wider area, high tensile strength, holding capacity, and environmental friendly properties. Next is pavement construction. Compatibility of geogrids in concrete pavements, since it can increase the durability of rigid pavements with its high flexural strength obtained when combined with concrete. Geogrids are also used to stabilize the subgrade for construction of embankment in highways, railways, and also in the stabilization of soil with low bearing strength to carry heavy loads becomes critical. Other than that, reinforced soil slopes also one of the application of geogrids. The same basic principle utilized in wall designs are used in slope designs with the exception of the facing. Since the face of slopes are generally not as stacked as retaining walls, different design elements are incorporated for erosion protection and aesthetic green landscaping techniques. And last but not least is reinforced embankments over soft foundations. Designers create this technique as a way to consolidate soft foundation soils. Doing so speeds the release of subsurface pore pressure and creates a foundation capability of long-term stability in a given time frame at a reduced cost comparable to alternate solutions.
There are three types of the geogrid. First, an axial geogrid. It is stretched only along longitudinal direction, thus the stress is transferred only along that axis. Even the tensile strength is more in longitudinal direction when compared to transverse direction in an axial geogrid. Second, biaxial geogrid. It is stretched along two directions, longitudinal and transverse. Thus, the stress is equally distributed along both directions. The third type of the geogrid is triaxial geogrid. There are four materials in the geogrid. First, polyester. Second, polyvinyl alcohol. Third, polyvinyl chloride. And the fourth, polypropylene. The installation guideline for the geogrid is material identification, material handling, geogrid placement, and the last one, placement of the fill material. There are 18 steps of geogrid retaining wall installation. Step 1. Planing the geogrid retaining wall. Mark the bottom and top of the geogrid retaining wall excavation location with spray paint or stave. Establish proper elevation point for both the bottom and top of the wall before starting excavation. Step 2. Excavating the geogrid retaining wall. Excavate and prepare sub-base leveling trench 6 to 8 inches below first course. This will be filled with good road-based material. Next, Step 3. Sub-base and base stabilization fabrics. Compact sub-base to 95% standard proctor density or greater. Remove any organic or poor soil in the sub-base and replace with proper reinforced fill material before compacting. Base stabilization fabric will help prevent sub-base material from mixing with gravel base leveling pad during compaction. Fabric also provides extra structure bearing stability to the base leveling pad. Step 4. Compact gravel leveling pad. Correct moisture content in the gravel will help in reaching proper compaction. Compact gravel leveling pad to 95% standard proctor density or greater. Step 5. Laying first course of magnet stone retaining wall block. Place a steel stake at either end of the leveling pad to establish the back of the first course of unit. Place each unit on top of the leveling pad in such a way as not to disturb the level gravel. Step 6. Complete base row installation. Step 7. Backfill the gravity retaining wall. Backfill the magnet stone block with an approved material. Run a plate vibratory compactor or a roller vibrating compactor over backfill material with proper moisture content. Backfill in leaf or layer that are acceptable to the soil condition and size of the compaction equipment. Proper compaction is crucial to the success of the finished product. Step 8. Drain pipe for geogrid retaining wall. A fabric wrap for perforated drain pipe should have adequate slope to drain water in the right direction toward its drain pipe outlet. Perforated drain pipe laid in the horizontal course can be soak wrap system to help prevent fine from migrating into the pipe. Step 9. Installing drain gravel. Clear class drain gravel is placed in the vertical and horizontal hollow course after placing and compaction of the backfill material. Make sure the backfill material directly behind the wall are placed flush to the top of the unit. Make sure the backfill material are well compacted and level as possible. Step 10. Installing Geogrid 2 retaining wall. Cut Geogrid reinforcement to the length specified in the design. Each project has specific cross-section with the length of the Geogrid should. Correct Geogrid orientation, strength and length is crucial to the success of the wall project. Each Geogrid length should be laid parallel and adjacent to each other but never overlapping. Step 11. Geogrid and connection with second layer. Place the Geogrid as far forward on the magnet stone unit as possible without revealing it on the face. Make sure each unit is installed against the unit next to it, leaving no gaps between unit joint. Use tape or backfill material to maintain the tension of the Geogrid during backfilling. Do not drive equipment directly on top of the Geogrid. Next, step 12. Backfill reinforced Geogrid layer. Backfill the reinforced zone by placing material from the back of the wall toward the end of the Geogrid. Install drainage gravel in the cross after placing and compacting backfill material. Install and compact backfill material in lift no greater than 6 inch. Check with the compaction equipment for maximum lift detail. Step 13. Backfill on and building your Geogrid retaining wall. Install third row of block following the same guideline as previous step. Step 14. Backfill and building your Geogrid retaining wall. Also, install fourth row of magnet stone retaining wall block following the same guideline as previous step. Step 15. Backfill and building your Geogrid retaining wall. Install third row of block following the step guideline as previous step also. Step 16. Top of wall unit. Complete the top of wall with magnum stone top unit. Magnum stone top unit are manufactured with the back panel 8 inch lower than the front page panel. The clear crushed drain gravel and backfill material will be placed flush to the top of lower back panel. There are times when more than 8 inch of topsoil may be required. Step 17. Soil separating filter fabric. Place a 6 feet wide soil separating filter fabric on top of the backfill and drainage gravel and against the back of the last unit before placing the planting soil. The fabric will prevent planting soil fine from staining the face of the wall and migrating into the clear crushed drain gravel. The last step is final grading of Geogrid retaining wall installation. Ensure that final grading is done on the top and bottom of the retaining wall. Make sure to protect newly placed planting soil from erosion during heavy rain or surface runoff.
And now I will explain about technological advancement, advantages compared to another technology and innovation. Alright, firstly we will start with technological advancement. As you can see, this is a two product from Titan Environmental Containment. This company established in 2006. They specialize in the supply and installation of high quality geosynthetics such as geomembrane liners, geogrid, geotextile fabrics, containment system, erosion control product, and specialty civil engineering product that all help manage and protect the environment. Alright, we go through the first speech first. The first speech is monofilament woven geotextile. It is produced by the Titans company. These geotextile are used in situations where high water flow rates are necessary. This type of woven geotextile is manufactured from extruded polypropylene monofilament, which are woven to create a very dimensionally stable and highly permeable geotextile. As filters, they have superior resistance to soil and biological clogging. As separators and stabilizers, they allow water to freely pass while preventing soil erosion. Furthermore, these monofilament geotextiles are primarily used to provide filtration underneath materials such as gravel, riprap, large stone blocks, geocell, interlocking blocks, paving bricks, or other types of erosion protection material. This function by restricting soil particles but allowing liquid and gases to easily pass through them. Alright, the second picture is the asphalt reinforcement fiberglass geogrids. This produced also by Titan, and these geogrid are designed specifically as an interlayer for asphalt reinforcement. This fiberglass geogrid system work to enhance pavement life and performance while helping to reduce maintenance costs. This include the fiberglass geogrid and the fiberglass composite geogrid and their newest cutting edge tech film fiberglass geogrid. While they have distinct characteristics and offer different benefits, they all feature a unique coating that provides excellent heat resistance and stability to a melting point of 900 degrees Fahrenheit, as well as very low shearing case and ultimate elongation to create a rigid asphalt layer, and highly durable. Biologically unaffected by soil microorganisms, inert to all chemicals normally found in the soil, and formulated to resist ultraviolet degradation. This geogrid, or it is called a TEFGP, is a polymer coated fiberglass geogrid featuring ultimate aperture size. It allows asphalt particle to penetrate through the grid to achieve high interlock and effective bonding of two asphalt leaves. Additionally, it is self-adhesive, which eliminates the need for tack coat and speeds up installation. And next, I will explain about the advantages compared to another technology. Alright, firstly, in the geomembrane category, it is highly impermeable. It is also flexible and high resistant to leachate. After that, the geosynthetic bentonite composite. It is low permeability, flexible, also self-healing to small cracks, and also easily available. Alright, lastly, I will explain about the innovation. And firstly, we optimize flexible wall system. Okay, it is mean that geosynthetic reinforced soil walls involve the use of continuous geosynthetic inclusions such as geogrids and geotextile. The acceptance of geosynthetics in reinforced soil construction has been triggered by a number of factors, including aesthetic, reliability, simple construction techniques, good seismic performance, and the ability to tolerate large deformation without structural distress. Then, recent advance in the design of geosynthetic reinforced wall and the availability of high strength products have led to systems that are particularly suitable for high walls. The second innovation is exposed geomembranes. Many of the cost and performance related concerns associated with the construction of conventional cover system can be minimized or eliminated by constructing exposed geomembrane covers. These covers are particularly suitable for sites where the design life of the cover is relatively short. Future removal of the cover system may be required. The landfill site slopes are steep, cover soil materials are prohibitively expensive, or where the landfill is expected to be expanded vertically in the future. Key aspect in the design of exposed geomembrane covers are the assessment of the geomembrane stresses induced by wind uplift and the encouraged requirements against wind action. Wind uplift of the geomembrane is a function of the mechanical properties of the geomembrane, the landfill slope geometry, and the design wind velocity. Also, wind uplift design consideration involve assessment of the maximum wind velocity that an exposed geomembrane can withstand, of the required thickness of a protective layer that would prevent the geomembrane from being uplifted, of the tension and strain induced in the geomembrane by wind loads, and of the geometry of the uplifted geomembrane. That's all from us. Thank you.